What I left off and was going to start doing next was polarization. That was it's the last main thing I'm worried about in chapter 29. So last new concept we haven't actually discussed. That'll be on your exam. Key with polarization. I'm sure all of you have heard of polarizers, Polaroids, so you probably already have a clue about this. Raise your hand if you own a pair of sunglasses, polarizing sunglasses. See, if I'm going to own sunglasses, I figure they might as well be polarizers so I can do cool physics instead of just, making it darker. My favorite accessory with my camera for photography is a circular polarizer. I love that thing. That's great. And it only works with waves. But polarization is a little different than these other things we've done with reflection, refraction, diffraction, beats, interference, superposition. All waves do those things, Doppler effect. But this only works with one type of wave, polarization that is. It only works with transverse waves. It doesn't work with longitudinal waves. So you can't polarize a sound wave, because it's longitudinal. You remember the difference? Since we're reviewing between longitudinal and transverse? Yeah, it's the direction of vibration versus the wave travel. So sound vibrates, say, this way and travels that way.
Could you say what a rarefaction is again?
Fancy word. Compression.
But that's only for longitude.
Rarefaction. Compression, rarefaction, compression, rarefaction. And it's just longitudinal.
And that determines the wavelength?
The distance between rarefactions or between compressions would be a wavelength, yes. For transverse, the medium moves, say, up and down, but the wave travels transverse to it, perpendicular, 90 degrees. And so from one of those crests to another crest, that would be a wavelength. Or trough to trough. Compressions, that would increase the pressure. Rarefactions decrease it, where they're spread out. And it does that in the domino effect. This will push these air molecules and they'll compress. And then they'll be, you get it. So polarization only works if it's transverse, because it does this directionality thing. So we learned that an electromagnetic wave, light, not just visible light, but ultraviolet, infrared, radio waves, they're made up of two things, an oscillating electric field and an oscillating magnetic field. So this is my model to represent those fields. Say there's an electric field oscillating in this direction, vertically. Well, why is that a preferential? The wave could be like this, or this. Well, it's actually vibrating in all directions. So you can have an oscillating electric field vibrating vertically and one vibrating diagonally and this way and this way. So these all represent planes or axes of orientation of an electric field, of an electromagnetic wave. They could also represent the magnetic field that's oscillating, but let's not complicate things. So say these are all the planes of an electric field oscillating. One's this way, one's this way, one's this way. We call this unpolarized light. Unpolarized. That's what most light is. The light coming from the lights above is unpolarized. So it has electric fields oscillating in all directions, like this, and it's coming at us. Well, these can interact with materials differently depending on the plane, the way the molecules are aligned. And Polaroids, we call them polarizers now, work that way. So here's a model. It's essentially like, if we simplify it, of blinds. They have slits. And the way the molecules line up, they're either lined in one direction, not in all directions. And so, say an unpolarized light wave comes in, which ones make it through? Yeah. Right? Only the ones in this orientation make it through. So now we say it's polarized light. So it's not in just any old orientation, it's vertically polarized. because we say the axis of this polarizer is vertical. Polarized light. You're like, so what? Well, you can do fun things with this. Let's say you had a second polarizer oriented vertically. Will it make it through? You bet. But what if you turn it 90 degrees? This one, the unpolarized light will come in. It'll pass through. Tighten it up. Now it's polarized. It can go sideways. But it can't get through this one because it only lets it through horizontally. And so you get no light out here. We can show that for reals. Let's do this one. So I mounted some polarizers above this overhead projector. So that is polarized light because there's a polarizer right here. This is a polarizer. So that's unpolarized. You can't tell. That's polarized. Notice it's dimmer. Well, sure. In order to block out about 50% of the light that's going the wrong way, this lets through light. It's by this tape. It's oriented vertically. So it only lets the vertically polarized light through. So it's a little dimmer. The horizontal is blocked. So I'm going to put that back in here. And it's coming out vertically. So it's still vertically polarized. A little dimmer. Take a second one. I'm going to align it parallel with that one. So it's vertical also. Little dimmer maybe, because these aren't perfect. But I'm going to rotate the top one. And there you have it. They're now crossed, polarizers. One's vertical and the other's horizontal. So just like my model over there, it can't get through both. So unpolarized light coming from the projector gets polarized by the first polarizer. It's polarized vertically right here. But this one's horizontal, so it can't get through. And you see a dark spot. That's polarizers. Here's some polarized sunglasses. You know. Yeah. And that's how they work. They're polarizers. So if I hold this up, let's put it over here so it's focused. Doesn't get through? Does get through. Doesn't. Does. Doesn't. Does. Let's see. This is how you'd wear them. Let's see, can we see it at all this way? You can sort of tell. Here, in normal orientation, it gets through. Like this. So these must be oriented vertically. And that's how sunglasses are. Because if I turn my sunglasses perpendicular, in the lenses, they're oriented this way, horizontal. The light's vertically polarized. It doesn't get through. It blocks it. Why do we do that? Just turn the lights up so you can see me. It's for glare. When you're wearing sunglasses, light that reflects a little bit. Oh, yes.
Why do polarized sunglasses show the color spectrum of certain surfaces like LED photospheres?
Why would you?
Why do so? I'm looking at my phone screen.
Sticky.
My sunglasses on.
Okay, I gotcha. I'll cover that one after this reflection thing. Light that reflects off of non-metallic objects, well, even metallic, various objects, even in the sky, when it reflects, can become partially polarized. And most reflections that we see, because we're vertical, say it bounces off of this piece of glass right here. Unpolarized light comes in, all directions, reflects off of here. The light that gets partially polarized gets polarized horizontally, because this is horizontal. And so it's in this plane, like this. Well, so I see glare. I can see the reflection of that light right now. But that light must be partially polarized entering my eyes, this way. If the orientation of your sunglasses is this way, then they'll block that partially polarized light. Yep, what do you know? That's how you can check if you got polarizers. You can go like this. Oh, and if you see a change in intensity, you know they're blocking some of the polarized light. But it helps out with glare off of roads when people are driving, or water, the reflections off the top, so you can see the fish underneath. But other things are polarized too, and so when you're wearing glasses and you look through a camera screen or off of some computer monitors, yeah, you're starting to see that polarization effect of blocking. They often do that for the angle. One reason could be for security, so that only if you're looking straight ahead you can see them, but at a funky angle you might get polarized. They can also do it for glare, because you'll get lots of reflections off that glass screen. But if it's polarized from behind, only certain amounts can get through. They do that with ATMs. CD readers, DVD readers use polarized light to block. And if it's polarized, you can block unwanted light and let what you want to come through. LED watches or screens, they use polarizers. Because light's coming in, but you don't want just all light coming back out, or the reflections off the top. If you polarize it, then you can block some of that light and only see the numbers that you want, or the letters. 3D movies do this too. They can use linear polarizers like this, or circular polarizers. And if you have, like, say, one lens that's vertical and the other lens that's horizontal, and then you shine on the screen both types, only one eye can see one of them. You know what I mean? The vertical one can get through the vertical glasses. The horizontal one can only get through the horizontal lens. And so you can send two different pictures, images, to the screen by wearing polarized glasses. You know, like one eye sees one image and the other eye sees a different image. Your brain puts them together and you can see 3D. It's like you're faking out your brain to add depth and illusion. That's one simple way to do 3D. Here's something I think's interesting. Let's put this one back in there. Douse the lights a little. Let's block the light. There we are. And I'm going to take a third polarizer. It's oriented this way. And I'm going to stick it in between. Doink. Hey, look, light gets through. What? It can't get through both of those, but by somehow inserting a third one, it can. I find that weird. It depends on where you rotate it, too. You remember I was talking about components? Back with forces? You could have a force that way. You could also have a force that way. Which way does it go? These are components of the resultant. It'll hit off that way. You can play the same game with the direction of a polarization axis. And so some of it breaks it into components, and some of it can get through. But just think of it this way. This has an axis, and it can rotate. The vertical polarized light is now kind of diagonal, and diagonal can get through horizontal because it's not completely perpendicular to it. Where this becomes fun is, here's some corn syrup. Certain materials will rotate the axis of polarization. Light slows down when it goes through materials. Well, if it's polarized light, depending on which axis goes through and which direction, one will get slowed down more than the other. And so instead of the light getting through all together in sync, one orientation is slowed down while the other one has kind of got ahead of it. Well, different colors transmit at different speeds, so they get rotated different amounts. The upshot here is polarized light gets rotated as it goes through these sugar molecules. And the different colors rotate at different angles. And so right now we're blocking the, well, let's see, let's make it easier to talk about. That's kind of a cyan color. So we know the polarizer is blocking which color? Cyan was blue and green. We're reviewing your color mixing for your exam. So red must be getting blocked. Rotate it some more. Oh, different wavelength. There's yellow. What's getting blocked? Yellow is red and green. So the blue wavelength's getting blocked by the cross polarizers. But I think that's cool. You can see color from Cairo syrup. How about, here's a CD case. Wow. Stresses in plastics and glasses rotate the axis of polarization. And so different colors make it through. Again, this looks magenta. That's red and blue. So green wavelengths getting blocked there. They got rotated to the crossed angle. It's being blocked. So you can detect where things are under a lot of stress. Where's this going to break probably first? Well, maybe over here. Let's try a fork. Let's do it like this. Get some cool color. And you can squish it. Let's stress it. I got a different pattern here. Oh, look at that. You can see it's going to break right there. It's under a lot of stress. And when I squish it, more stress rotates them differently. Here I tightened some nuts on some screws. Can you tell which one's tightest? Squishing the plastic? Well, that one, it looks like there's more stress there. Even my glasses work. I should not be focusing while I have my glasses off, should I? All right. Can you rotate a little different? Look at that. My glasses will probably break first there. Architects have used this. They've built small-scale models out of glass or plastic, and then sandwich it between cross polarizers, shine light, and you can see the stress patterns. See where the forces and the tension and the strain are greater. All right, another one. So here's a plastic tube, hose. All right, let's see any color. How about there-ish. All right, let's stretch it. Let's twist it. Oh, yeah, that's cool. But anyway, that's what some fun things with polarization. It only works for a transverse wave. And when they're crossed, you can block it. Now we're going to review some electromagnetic radiation. All light would do this. Here's a little shortwave radio transmitter. Turn it on. Yes, it uses vacuum tubes. What it's doing is it's oscillating electrons back and forth on the antenna. And I don't want to touch it because it hurts a lot. And so this is a transmitter. This is like your radio station. Because the electrons are moving this way, this will cause an electric field to oscillate in the horizontal plane. Radio stations and transmitters emit polarized waves. This one's polarized horizontally. Here's my antenna with a little light bulb in between. If I can get that wave to make charges in here oscillate, you know what's going to happen. Then they'll go through the light bulb. Well, look, it doesn't light up. That's because the wave's changing like this. I'm rotated. Let me turn it. There we go. I'm picking up the polarized wave because the transmitter and the antenna are aligned. What if I turn it vertically? No, because it's a polarized wave. It's brighter when you're closer to the transmitting station, and it's a little dimmer as you get farther away because the power dissipates with distance. But there's a polarized electromagnetic radio wave.
And it needs to be on that level for that frequency. So it's just coming out in all directions.
Yeah. I mean, it doesn't stay. You can have one go right above it. I mean, it's oscillating this way, right? So it can go up also. But it's polarized in this direction, whether it's over here or up here. Let's see. Yep, not near as strong. If I could get taller, far enough away.
And so it doesn't hurt you holding that, obviously.
No, the power is, by the time, the amount of power that gets to here, yeah, it's safe. I'm not going to touch that though. My predecessor, I haven't touched it yet, but he told me he accidentally touched across there once, and that's the only thing that's knocked him flat on the floor. So I'm not doing it.
Is that like my little AM radio where you have to turn it to get the best signal?
Oh, I'm glad you brought that up. Yeah. Let's use that to review. AM radio versus FM. You remember the units for frequency? Right, and we did that before. Kilohertz, megahertz. This one's FM, frequency modulated. This one's AM, amplitude modulated. You know the difference between frequency and amplitude now. This is how the rate it vibrates. This is the maximum amount of displacement from the equilibrium position. So this is amplitude, or this is amplitude. Here's a wavelength. And the time it takes to oscillate from there to there again, we call the period. And it's related to the frequency how? Yeah, inversely. That's time. This is cycles per second. One cycle takes so many seconds. So it's in hertz. So back to here. Which wave is longer? There's a relationship between the wave speed. Do these waves transmit at 340 meters per second? Or, what was it, 300,000 meters per second? Is it the speed of sound or the speed of light? Good. Speed of light, because this is a light wave. It's an electromagnetic transverse wave. The sound that comes out of your stereo that you hear is moving the air around. That travels at that speed, through air, at room temperature. So the relationship is frequency times wavelength. You'll want to know that. So which wave is longer? AM or FM? AM. It's vibrating more slowly, has a lower frequency, and those are bigger waves. Because if this is the same for AM and FM. They're traveling at both at the speed of light. But if the frequency is smaller, the wavelength's bigger waves. Why did I bring this up? Oh, I brought this up because just a second. Distracted. Your antenna. On your little radio, you pull up your antenna, right?
It's just in the body.
Well, yeah, a lot of them have the antennas, or on your car. That picks up the FM because they're shorter waves. Your antenna would have to be absurdly long to pick up these big waves. So what they do, instead of picking up the electric field with a conductive antenna, they pick up the changing magnetic field. There's a coil in there that when the change goes through, it makes a current flow in the coil. But the coil has an orientation also. So when you rotate your radio, same exact idea as what we just showed with this electric field polarization. Yes?
Yeah, is it the wavelength is the one which affects the clearing of the AM?
The wavelength's different, yes. And so with the frequency then as well.
So when it is short, that way it is clear. And when it is long, that way the sound is... Sometimes when I listen to AM, the sound not clear like when I'm
Oh, why? The quality of the two is changed. That has more to do with how it's modulated. The quality between the two. Sometimes this one usually doesn't sound as good as this one. And that's because basically, remember from Morris's class, am I getting it right? This just isn't as good as that. But there is an advantage to AM. Bigger waves versus shorter waves. Which one will transmit farther? AM, because longer waves. Why? Less interactions. The shorter waves have a higher frequency, so they're interacting with the medium, anything, more often. And every interaction transmits some of that energy, converts it to thermal energy. And so high frequency short waves don't go as far as longer ones. So you can broadcast this a lot further, even though it might not sound as clear. And at least you can get a signal.
I've always heard that the AM bounces off the atmosphere, whereas the others go through.
That's true. The reflections have to do with the medium as well, right? We learned about transparent and opaque. These have different frequencies and wavelengths, so they reflect off of various materials differently. Yes. The ionosphere, and whether it's day or nighttime, yeah, the atmosphere changes. Very good. Okay. I should at least mention holograms. They're really cool. This is the last thing in the chapter. I won't test you on it. You should at least know holograms work because of diffraction. You've probably all seen a hologram. Basically, it's a film. Think of it as a diffraction grating. The waves go through and they diffract. What's that mean? They spread out. But then those different waves, the wave that spreads out from this side and the wave that spreads out from this side can do what? They overlap, superimpose. They can interfere constructively or destructively. And the pattern of that diffraction grating is essentially reproducing the image that created it. That's a hologram. It's like some film. They like etched an interference pattern in the film. So when you take light and shine it back through it, it diffracts and interferes again in the exact same way it was formed, and you see an image that they used to make it. That's what a hologram is. It's just diffraction and interference of waves. It's cool. And that's all I care that you know about a hologram. Yes, Lee?
So, like, a light wave is electromagnetic and it's transverse. Are those always related, or can, like, electromagnetic waves be longitudinal also?
Electromagnetic waves, or the electromagnetic spectrum.
Yeah.
So radio, microwave, ultraviolet, visible, infrared, cosmic, X-rays. Those are all transverse waves. They're the same kind of wave. They all travel at the same speed. They would never be longitudinal. They don't need a medium to transmit through. They're not mechanical waves. They drive themselves. They all have an oscillating electric and magnetic field. And what's the same? I already said that. What's different about them, though, between them? Yeah, kind of like this. These are two waves, but the frequency or wavelength can be different. But they look the same. One just might be where one's...
So, like, sound is longitudinal.
Sound is longitudinal.
It's a medium, but, so can, what's it called again?
Mechanical wave?
Mechanical
Mechanical waves need a medium.
Okay.
They got to make something vibrate in order to make it transmit. Light and electromagnetic waves, all of them, don't need anything. They can transmit through empty space. That's how light gets to us from the sun. So let's see here. I'll up this a little. Till I get to it. So, chapter 19 was vibrations and waves. Way back when. The source of all waves is a vibration. That's right. We started with a pendulum. I want to remind you about those, since that was so long ago. You got a pendulum that swings. It's a certain length, it has a certain mass. There was a relationship for how long it takes to swing. It's based on certain things. It's proportional to certain things. Do you remember what those are? That period is proportional to... What's it depend on? The length. If we made it longer, it's covering more distance, so it takes a little. The period increases. Yeah. What else did it depend upon? Not velocity, but it had something with motion. What's that? Yeah, gravity. The acceleration. Because if you displace it over here, its gravity, it has a weight, it's being accelerated down, and how fast it's being accelerated will determine how fast it swings. You go to Jupiter, this would swing faster. So yeah, and that was inversely proportional, because if you make it more acceleration, the period will be quicker. So if G's bigger, T will get smaller. What did it not depend upon? Mass, right. That was irrelevant, because everything's, we learned long ago, all masses accelerate at the same rate. Big or small. That's why they hit the ground together, barring air resistance. Wave description, we kind of already did that. You'll want to know all this stuff. Oh yeah, standing waves. You can send a wave forward, since I already drew it over here. And it can bounce off the end of a tube or a string, and it can reflect back. So you have an incident wave and a reflected wave. And if they constructively interfere, it formed a standing wave. Remember that? So say you got a wave going, it hits here and comes back. And so it looks like it's just kind of going up and down, not side to side. It looks like it's standing still. Do you remember what the terms were called? How about these spots where it doesn't seem to be displaced from the equilibrium? Yeah, those are nodes. Good. What are the other ones called? Antinodes. That's the positions of maximum displacement. So here, 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 and there. Don't forget there's nodes on the ends. They wouldn't be moving if it's tied off there. That was just some definitions, but it was a while ago. Doppler effect. What does Doppler effect work for? All waves, that's right. Pretty much everything we discussed works for all waves, except we just did it. Polarization only works for transverse. The Doppler effect, does that work when, what conditions would you hear that in? Or see it? Relative motion, good. Do we away or towards or what? Both, right, whether you're moving away or not. Whether one's moving, you're moving, or I'm moving, or we're both moving. Yeah, relative motion between objects. We had, what do we have? Bow waves and shock waves. Bow wave was just the two-dimensional version. Shock wave's the three-dimensional version in a cone. That was when the waves start shifting. So say you have a source that's made a wave, and if it's not moving, they just keep going out. But if the source is moving, its speed compared to the speed of the waves, you can overtake them, can't you? The Doppler effect is when this speed is less than the waves. And what happens? They kind of, if I can draw it, they get smushed together here. That's why the frequency increases as it's coming towards you. And they get spread apart here. But if you're going even faster, what forms? Yeah, a bow wave, which it's a lot harder for me to draw. Good enough. I won't push my luck. So the source is moving faster than the waves, and you get a bow wave. Remember that? It's the superposition of all the wave fronts right here. If you're standing here, what do you hear? This is a pilot cruising faster than the speed of sound. And he's passing by you, and you're standing there. What would you hear? Good. It was a trick question. Nothing yet, because the waves haven't reached you. What if you're right here? All of them at once. And that amplitude, they're all going to superimpose and add, and that'll be really loud. Or bright, if it was light, and you could do that. We talked about that. What if you're over here? Yeah, it's already passed. So you heard the loud sound, but not anymore. What's the pilot here? Are any of those wave fronts passing him? No, he doesn't hear the sonic boom. They called it the sound barrier because they thought as you go faster and faster, at some point you pass where they all are together and you're going faster. And they thought you couldn't break through it and then it'd be really loud. But no, because this wavefront never passes that person. He's Adam. He'd be Adam, and now he's ahead of him. So if he slowed down, he could hear these, but he wouldn't hear the bow wave, the front there, because that would never pass him. Maybe if he could do some funky maneuver where he curves really fast, slows down, and then this wave, then yeah. Then chapter 20 with sound. And if you got specific questions, throw them out too. I'm just trying to jog our memories, tell you what's important. We did range of hearing. We can only hear certain sounds. It was 20 to 20,000 hertz was our range of hearing for a healthy ear. I'm already down to 16 or 17,000. I can't hear above that anymore because it's damaged to our ears. Too much loud intensities and the amplitude drove my ear too much, and they've been damaged and they don't grow back. So those high frequencies I don't hear as well. We started making these waves, and specifically sound, transmit through things. How does sound travel in air compared to water? Not as fast. Why?
There's less interactions for it to bounce off where water does much easier. Same with steel, there's a lot more interactions quicker.
There you go. It's the interactions in water or steel compared to air. Yeah, there's more interactions. Remember my dominoes? If there's more interactions, that's going to get transmitted faster because it's the medium. It's a mechanical wave. It's trying to vibrate those, so that actually transmits it faster. As opposed to light. Remember light? Light doesn't need that. So it's actually a hindrance. And when you go through something like water or steel, well, not steel, but water, glass, those interactions slow it down. But it speeds it up for sound. So in general, the more dense an object, the faster sound travels through it because of those interactions. Or if something's hotter, right? Warm air versus cold air. Sound travels faster in which? Who's going to have more interactions? Warm. So it's faster in warm. Because they're moving around more, so there's going to be more interactions.
What do you think about the particles being condensed together?
Yeah, and we mentioned that earlier, and that's a play too. Warm air is less dense than cold air, so that alone would make it go the other way. But the fact that they're moving faster dominates, and so what we just said, go with that. Yeah, that one can be confusing. Where are we at? What else do you need to know about? So then waves, we started reflecting them and refracting them. Say you got the warm air or cold air, right? Let's say cold air and warm air. And you got a wave front coming. Okay, which way will it bend? You got a light coming in. Okay, we just said, let's say it's sound. Sound's coming in, it travels faster and warm than cold. So this wave this part's going to get ahead of this part because it's moving faster. So it's going to start doing this, right? That's refraction. You're changing mediums from warm to cold in a sense, and it bends. But that's how you remember which way it bends, which one's it going faster in, which one's it going slower in. You play the same game with light, you just have to remember that instead of speeding up, it slows down, or vice versa. Then we did a bunch of vibrations. Well, we've been vibrating all along, but driving something. Do you remember a forced vibration? That's like plucking a string on a guitar. You're forcing the string to vibrate. It's attached to the wood, and you're forcing it to vibrate. The string, based on its length and tension, will naturally want to vibrate at a certain frequency. So you have natural frequencies. So you'll cause the vibration by strumming it, and it'll naturally vibrate. But it's attached to the wood, and it's forcing it to vibrate. If those two match up, we call it resonance, right. And that works with sound, objects in general, and light. Remember when light is at resonance? If that incoming light resonates with a material, what happens to the light? It gets absorbed and the internal energy increases, right. It's not reflected or transmitted. So that tells us whether something's transparent or opaque, right? We did shadows. Pretty simple. There's two parts to it. Say that's the Earth's shadow blocking the sun's light, right? But there'll be a darker spot inside. The umbra and the penumbra, or full shadow, partial shadow. And if this covers the moon, you got a total lunar eclipse coming up on April 15th. And if it was over here, it's part of the moon's in partial shadow. Some of it's totally blocked. It'd be a partial eclipse. There's just two parts of a shadow. And this shadow happens because light's coming around the edge of the Earth, right? And when waves go around an edge, what does it do? It diffracts. Yeah, diffracts. And something I didn't make clear, I want to, is diffraction with waves. So let me make some color. Oh, let's put this one in. There we go. This is refraction with an R. Who gets refracted more? Violet and blue. See how it's bent more? And that was because it's vibrating faster, the frequency's higher, so there's more interactions, so it gets slowed down more. It's affected more, so it bends more. It refracts more. We discussed that. Here's a diffraction grating. Bunch of slits. So the slit ends up here. Who gets diffracted more? Diffraction. Who gets spread away from... Here's the straight shot. Who gets bent away further? Spread out more. Yeah, red. It's opposite. That used to confuse me too. What I didn't emphasize well enough yet was the size of the waves or the frequency affect that, just like it did with refraction. The light's trying to go through these small little openings, a bunch of little slits, edges, so it's spreading out. Who's going to get affected more? A big wave trying to shove through a little opening? Or an itty-bitty wave trying to get through that same opening? Who do you think gets affected more? The big wave. It's harder to fit. And who has the bigger waves? Red. Lower frequency, longer wavelengths. So they get diffracted more. Longer waves are diffracted more. You've experienced this with sound. Somebody brought this up before. How you can hear sound around a corner. That's the point of this little demo. Here's a speaker. Here's a baffle with a hole. I'm going to bring it up to the hole. Do you hear a difference? Now focus. This sound compared to that sound, if you had to classify it, does the pitch seem to change or just the loudness? It's definitely louder. To me, it sounds like the bass notes are louder than the treble notes, the lower frequencies. What's going on is this puts them, whatever it puts out, big waves and small waves. When it comes up to here, where it's focused, and this is blocking. They put speakers in a box for a reason. It's because the sound waves that are coming out this way diffract around the edge of the speaker itself. They bend. Which waves bend more, diffract more? The bigger waves, the longer waves. So in that case would be the low notes with the lower frequency, big wave, small frequency. So the bass notes are diffracted more. If they diffract, the front of the speaker is pushing this way, while the back of the speaker is going forward. So there's a compression in front and a rarefaction in the back. They're out of phase. They can interfere. The bass notes will diffract more than the treble notes, and so they're out of phase. They cancel each other out. And you don't hear the bass notes as well as when you put it here and stop them from diffracting and interfering. And it works whether you're this way or this way. So I thought that would be a fun practical example for some of you to reemphasize diffraction. Longer waves are diffracted more. They're affected more. All right. 4 minutes. I'm going to dispense with the clicker questions then. I had a few, but I've covered a few of them, reviewing. See, that was everything but color mixing. Now, we had additive and subtractive. I mean, that
That threw me on the homework.
the red, green, and blue light added together. It's all laid out in your book. We've kind of had some examples. Red and blue together make magenta. I fixed this, so let me show you that for some of that review. I've tested it lots. Watch it not work. Okay, good. So what color does this ball look? Whitish purple? All right, what color does it look now? Red, green, and blue. This has red, green, and blue LEDs inside of it, and they flash in sequence. So one turns on, then it turns off, next one turns on, red, green, and blue. So if I displace the ball like that, you can see them flash in turn. But they're flashing really quickly, too fast for our eyes. So when they're all together in the same spot, red, green, and blue light go into your eye, and this looks mostly white. The red's a little too strong. But I can just go like this. Or you can even wiggle your head, go like this. And you can see the effect that way. That's additive color mixing. We're combining lights, and they mix as we've discussed. Pigments are subtractive color mixing. And they will filter out some of those colors. So for example, if you see something iridescent, you've all seen something iridescent where you see shimmery colors like oil on water or soap bubbles. You see those fun colors. Well, it's like we did with the stress lines. If you see magenta light, well, that means red and blue are combining. So something got filtered out, either absorbed by a pigment or destructively interfered because they were out of step, out of phase. Magenta was red and blue, so green got filtered or subtracted away from it. That was the whole point of that chapter.
So then I have a question. It is part of our homework, so on number 20 it says rate interference filled with oil on water is seen to be yellow to observers directly above an airplane. What color is the appearance?
That was number 11. 20? Just so I can repeat correctly. So if you didn't hear him, because of wave interference, a film of oil on water is seen to be yellow to observers directly above in an airplane. What's that mean? That means yellow light's coming up. What colors make up yellow? Green and red. So that's coming up. What color's not coming up? Blue. So what color does it appear to a scuba diver underneath? Well, if the yellow's going up, something happened to the blue. He must see blue. Is the point of that one.
Yeah.
Yeah, you always deal with the pigments and subtractive, and scientists always deal with light, because it's all about light, and pigments just subtract light. So yeah, if you're more of an artist, that'll take you longer to get it together. So I would say red, green, and blue are the primary colors. You'd say they're what?
It's red, yellow, blue.
Red, yellow, blue for pigments. I would call those the complementary colors. But instead of being red, yellow, and blue, technically now you know that's not red, it's magenta. It's not blue, it's cyan. There's a subtlety there. And if you think of it that way, you can see how it filters everything out, and everything we've discussed would make sense. So think about it that way. I'll do one more demo for you here, since I know we're out of time.
Pigments, by that is the same thing as paint?
Pigments or paint. Here's water. Flip it over, just because I wanted to show you this. You wiggle it. Look what was hiding in the water. If light doesn't bend due to refraction, you can't see anything. And what causes refraction? Change in mediums, which makes the wave travel slower. It changes the speed. So if it doesn't change speed by changing mediums, because it travels the same speed in both mediums, like these water balls in water, it doesn't bend the light. And so you can make them disappear because none of the light's refracted. The invisible man. There you go. All right, come up if you got other questions. Email me, see me tomorrow, something, and I'll see you Friday.